Okay, now so many other examples, workbook examples in the similar way. Fixed beam subjected to central point load, I values are different. Then positive area by EI is equal to negative area by EI. You calculate it, finish it off. Now, these are the 7 concepts or the fundamentals necessary for the moment distribution method. Now, on these 7 concepts, how the numericals will come? Let us see. The basis for MDM are these concepts only. On the first concept, first let us see. First I told you about carryover moment, how the questions come. Moment at A is now let us say this load is 20 kilonewton. This point let us say A, B, C. This is say 2 meters, let us say 4 meters. Now you are given a propped cantilever beam. We want to find what is the moment at A. SM we have learnt that the effect of the point load at any other point will be a load and a moment developed by that load about the point. So I can remove and replace. So I don't want to deal with the overhang because my aim is moment at A. So this overhang you can cut, and whatever overhang does on the support at B we can show. So when you are cutting and throwing it out, what it is doing at the cut point you have to show. So I'll draw like this. This is the B. So the effect of 20 at B will be 120 kilonewton down and a moment like this. 20 kilonewton down because I am keeping it here. Then effect of the moment is 20 into 2, 40 kilonewton meter. Now this point is say A, B, 4 meters. Due to this load, moment, the deflection profile is like this. As I told you earlier, whenever you see this type of deflection profile, half the moment is carried over, that's all. This 20 directly transfers to the support B. This 20 has no influence on the beam, directly transfer to the support. But this moment, because of this profile, far end is fixed, half of the moment is carried over. That's what we told you about the carryover moment. So, half the moment is carried over means MA is nothing but M by 2, 40 by 2. 20 kilonewton meter clockwise. So, one of the option is 20 kilonewton meter clockwise. 4 will, direction also is important. 20 kilonewton meter clockwise, 20 anti-clockwise, 40 clockwise, 40 anti-clockwise. Like that they ask. So, how much movement? Which direction? This is about movement at A. That's all is for 2 minutes time. In the exam, questions will be so simple that if you understand the fundamentals within 10-15 seconds or some calculation intensive, little calculation is there say, 1.5 minute maximum you can complete in GATE. But in the prelims, maximum of 30 seconds you can complete in the engineering services prelims. Now you want to find say reaction at B or POC where the POC occurs. Point of contraflexure occurs at. Same problem, we'll take it now. This is 40. This point let us say A, B. The 20 direct transfer you don't have to worry. MA also just now you calculated 20. When you are finding the points of contraflexure, if you know the end moments, it is enough. Then what is the reaction developed? Because of the support reaction only, finally it became 20. Otherwise, if it is 40, here also 40 could have been there. So all support reactions also taken care of, it became 20. Again, you don't have to find support reaction to find the POC. It will waste our time. Also, you don't have to take a section XX, then bend moment at XX is equal to 0, then get an equation, solve it for X. That is also waste of time. If loading is not there, end moments are known to us, then draw a bend moment diagram. That bend moment diagram will tell you where POC is. By inspection, we can make it. See here, this length is 4 meters. Okay. Now, how to draw a bend moment diagram? I cannot find bend moment at RHS of B because when you stand there, you will fall down. Bend moment at B, indeterminate, couple is there. So, bend moment at LHS of B. Stand there, look right side. Section right side clockwise, it will hog. So, 40 down. Now, here, bend moment at RHS of A. Stand at RHS of A. Now, you have a choice. You can see left or right. If I look right, I should know reaction also. Why headache? Stand here, look left side. Only moment. So, section left side clockwise, it will sag the beam. So, it will sag, it will hog. So, same clockwise movement can sag the beam or hog the beam depending on its location. Okay. So, this is 20, this is 40. Then this is magnitude 40. When load is not there on the beam, only moments are there, the variation is linear. So, it will go something like this. This is plus, this is minus. This is the bend moment diagram. He is asking where is the point of contraflexure. To find the point of contraflexure, you can linear interpolation. This you take say x, the remaining distance is 4 minus x. So, I can write x by 20 is equal to 4 minus x by 40. 2x is equal to 4 minus x. So, 3x is equal to 4. X is 4 by 3. That means 1.33 meters from fixed end. So, in 2 minutes time, if they ask you what is the point of contraflexure, first cut, remove it off, here put 40, 20, then draw this diagram. First you have to find what is the moment at A, then only you can find POC. Okay. Remember that most of the questions come these 5 concepts what I have told you. Every year one question compulsorily will come on these fundamentals, MDM fundamentals. So, this is your bend moment diagram. That means you should be familiar to draw bend moment diagrams quickly by saying that this is the process. You should not write bend moment, take a section XX, bend moment at XX is so much, then at x is equal to 0 so much, x is equal to a 4 meters so much. That stories should not write. Stand here, look one side. How much is the moment? Put it. Stand here, look left. How much is the moment? Draw a line. Should not take more than 10 seconds time. Okay. Now, let us see what are the support reactions at B. This I remove. This also I remove. Now the fresh question, reaction at B. Support reaction at B is, to find that again same process. First remove the overhang, replace it by with its equivalent force. Now here there is a downward force 20, moment 40, carryover moment 20. This is COM. Okay, this is the structure. Now you have principle of superposition. That means individual effects can be added to get the final effect. So this we split into two parts. First, due to 20 alone, what are the reactions? This we know from strength of materials how to calculate. So if you have say 20 down, due to this reaction, what is VB? Vertical reaction at B is 20. Let us say VB1. What is VA1? 0. Because direct transfer of the load, beam will not be affected at all. Plus now the moments 40 and 20, both you are right. 40 here, 20 here. Now you see, this is 4 meters. Now what is the total moment? 40 plus 20, 60. 60 clockwise. To balance it, anti-clockwise. See how our fingers are moving. Anti-clockwise means down, up. So here it should go down. Here it should go up. Let us call it as a VB2. This we call it as a VA2. So M by L, we know total moment is 20 plus 40, 60 by 4. So you will get 15 kilonewton down, 15 kilonewton up. Now from the principle of superposition, add them. This you are writing from the principle of superposition. Now total reaction VB is nothing but VB1 plus VB2. So you will get 20 plus 15, 35 kilonewton upward. Then VA, VA1 plus VA2, 0 plus 15 down. So you will get 15 kilonewton downward. So they can ask you VB or VA, whatever it is. Now you see, your applied load is only 20, but reaction developed is 35 at B. That means reaction can be more than the applied load depending on the structure, depending on the where you have applied the load. Now in the process what happens, here if you take it, VB is 35, here VA is downward 15. So total downward force is 20 plus 15, 35, upward is 35, and MA, here you got it as clockwise, this is 20. So final reactions are 20 kNm, 15 down, 35 up. Now you see, if at all you keep a support here, in that support more than the applied load reaction will develop. A similar situation will come in the design of steel structures where prying action will be there. Prying action means, supposing that we have a T section, this one plate, okay. Now you have like this, you have taken one section, let us say, and you have welded, you apply some load to T, some T you have, this is a welded one, and you have bolted here, here also you have bolted. This portion is like a overhang similar to this one. When I pull it, if the thickness of plate is sufficiently large, then this type of separation will not happen. Assume that thickness is less of this T connection and you are pulling it, it went down. When this is going down, this overhang will go up. Here why the reaction is downward? Because of this one. When you apply this load, the deflection profile is like this. Like this. If the support is not there, it will go up. But support will not permit, it will pull him down. Come to this one. If this overhang is not there, simply it will come down, that's all. Because of this overhang, it will try to go up. But this fellow will not permit, it will press him down. So, what will happen? Like this downward reaction, this black color plate will exert a downward reaction some Q. Here also it wants to go up, but black color plate will press him down with a force Q. So total downward force is 2T plus 2Q. So bolt reaction is T plus Q. Here also bolt reaction is T plus Q. You see, your applied load is 20, but reaction is 35. Here also your applied load is 2T, but reaction is 2T plus 2Q. More reaction will get in the bolt. This additional force, whatever you get, is called prying action or prying force. That prying force is because of the flexibility of the connecting elements. Here this is because of this flexibility, it tries to rotate. Once it is trying to rotate, this will try to go up. If it will not go up if this will not go down. If it remains horizontal only, say, that means for it to remain horizontal, thickness must be large. So we will learn such type of prying forces and prying action based on this understanding. Okay. This in the design of steel structures, I will again explain how the prying forces will develop in the T connections when they are pulled. In this case, Q is a prying force, or Q is called prying force. Okay, this in the steel structures part we will discuss. That means just to tell you that the reaction can be more than the applied load because of the flexibility of the elements. Here, because of the fixed support, it is not permitting the beam to go up. Naturally, here the overhang support reaction will be more than the applied load. Okay, now let us see next case. Moment at A is now we will take one floating hinge problem. Here it is subjected to a symmetrical loading of say 60 kilonewton. This point let us say A, B, C, D, E. Then this is say 6 meters. This you can take say 2 meters, 2 meters, 6 meters. This is floating hinge. Internal floating hinge. Okay. Because the structure and loading are symmetrical, this 60 will be shared by ABC beam, CDE beam equally. If at all lengths are different, this is 3 meters, this is 2 meters, like that say, then they will not share equally. You have to calculate from the compatibility condition. Okay, that will take say 3 to 4 minutes time. So this ensure that both of them are equal. So now because now ABC will take 30, CDE will take 30. Now this portion here, it will take only 30 kilonewton. A, B, C. This is 2 meters, 6 meters, let us say. Then the other portion is C, D, E. C, C, D, E. Here now again 30 kilonewton. So in the strength of material, sir might have told you hinge reactions. If on one beam hinge reaction is downward, another beam hinge reaction is upward. But they are hinge reactions. Reaction exerted by one member on the other member. But here it is not a reaction, it is applied load. Then your applied load will be shared by the two beams in the ratio of their stiffnesses. That means in the how much deflection will happen, or whether if loading is symmetrical or not, how much they offer resistance we can find. So in this case it is the action, 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 no reaction here, because one member to other member nothing happening, that 60 you went and applied, then both will share. So on both the segments of the beam, load will be downward. When you take it and stick it, total will be 60 and it should tally like this. If load is not there, say some loading is here and there, then on this hinge, this beam, what it, when you cut it, you should show free body diagram, what this is doing on this one, upward reaction. Then this will do on this downward reaction. Then when you attach them, both should cancel out when there is no external load. But this is external load is there, so when you add them, it should be equal to that. Just I am giving you an idea that if I put 30 down here, 30 up, you used to put it, the reactions, but this is not a reaction. Okay. Now we are interested in moment at A, not in that part. So cut it, throw it out. Now take only this segment. So this is now equal to this one. 30 down, 30 into 2, 60 clockwise. This is 6 meters. Now out of 60, how much will be transferred? MA is M by 2. 30 kilonewton meter clockwise. This is one of the options in the exam. In 2 minutes, in one of the GATE papers, they asked a similar question. Load is different, spans are different, but symmetrical. So in 2 minutes time, you should understand that this will be shared 30, 30, 30 replace it here, and out of 60, how much is transferred here. 2 minutes time. But once you know the process, it will take hardly 15 or 20 seconds time. Okay, this is about the moment at A. Now, if at all the load spans are different, then how to manage? Deflection at C in ABC beam must be equal to deflection at C in CDE beam. So delta C1, delta C2 must be equal. That is a compatibility condition. So those deflections from strength of materials formulas we have to apply and find the relationship between ABC beam takes say W1, CDE will take say W2. W1 plus W2 is 60. Then due to W1 alone, what is the deflection at C? Due to W2, what is the deflection at C on the CDE portion? Then equate both the deflections, then W1, W2, how much you will know. Once W1 is known, instead of 30, suppose it is 26 kilonewtons say. Then accordingly 26 into 2, 54, then you transfer it. 52 and that you transfer it to other end. Like that. So compatibility condition we have to use it. In one paper they kept UDL. Moment at A is This point, let us say A, B, C. This is 10 kilonewtons per meter. This is 3 meters, let us say 4 meters. So, when you equate it, whether UDL is there or point load is there, it hardly matters. So, 10 into 3, 30. So, 30 down. 30 into 1.5, 45 clockwise, right? Because UDL acts at its centroid like this. This is 1.5 meters. This is 30 kilonewton. So, 30 into 1.5, 45. If it is 45, MA is M by 2. 45 by 2. You will get 22.5 kilonewton meter clockwise. So, this is the option. So, that is the process. Now, on the second concept, I told you about the carryover factor. Carryover factor means carryover moment at one end by applied moment. That ratio we have to calculate in 2 minutes time. Let us see how to find the on the second concept, how to find the carryover factors. Let us see. Carryover factor CAB is this is a problem. Let us say this point A, B, C, length is L and L. CAB means this one. Second letter is carryover moment. That means carryover moment at B by applied moment at A. This is the meaning of CAB. CAB means at A we are applying the moment, at B you are finding the carryover moment. Okay. Now how to manage? This is the problem A, B, C. Now you go and apply a moment M at A. This is M. This M is some moment applied moment. But when there is a floating hinge, we don't know how to manage how much moment at B is developed. This is like an unmanageable problem. First you have to convert into manageable problem. Means the problem which we know already. So if hinge is not there, we know how to manage. So cut here, remove it off. So first you will take this portion up to here. This only if you have, you know how to manage. If there is a moment M moment is there, because this structure is in equilibrium, any small piece you pluck out of it individually, this also must be in equilibrium. If M is clockwise, how the reaction will develop? Anti-clockwise, because hinge cannot give any anti-clockwise moment, hinge pin it is. So if this is clockwise, anti-clockwise reaction will develop like this. This is VA, M by L. VC is also M by L. Who will give this red color force to the black color beam? CB member must exert on AC member a force of M by L like this. If this fellow cannot give to this fellow this much force, it will fall down. Okay. Now let us see this member. This is CB. When you are drawing the free body diagram of CB, on CB what others are doing you have to show. If this is the force exerted by this fellow on him, what this fellow will do on this fellow? Will exert a downward force of same amount. Now when you take and shunt it, they balance themselves. reaction is 0, means external load is 0. Due to m by L, this length is L. How much moment will develop? This is anti-clockwise. To balance it, it should be clockwise. MB. So m by L into L, you will get m. Now this is carryover moment. Why? The reason for development of this m is this one. Since you do not know how to manage, you split it into parts and internal reaction is given. This is not applied load, it is internal reaction somehow developed. So due to this, this happened. So this is the reaction. So carryover moment. So carryover moment at, see both of them, this m and this m, both of them are clockwise. So carryover moment at B is plus m plus m. So you will get 1. So 2 minutes time you should be able to draw this diagram. You see here again one more point. Hinges, at the hinge point moment is 0. When here moment is 0, what is the moment? Here it won't be 0 because moment is 0, but it will transfer reaction like this. That reaction produces some moment. See, if at all you draw the Bend-Newman diagram, that Bend-Newman diagram will go something like this. Though all of you have known, I am just giving you that point how the, this is m, mb is also m. So when you draw the Bend-Newman diagram, it will go something like this. At the pin, this is m plus m. Here it should go down, plus minus. See, at the pin connection, Bend-Newman is 0. This is how the Bend-Newman diagram goes for this problem. Now you see, instead of connecting, if nothing is mentioned means EI is same, we have to take it. Supposing that no pin is there, but they give you this EI value, say infinity. Sir might have told you, if flexural rigidity infinity, it implies that it will take moment, but it will not bend. It remains as a straight line. So let us see how the beam of infinite stiffness behaves. This is again a 2 marks question. Carryover factor CAB is this point A, this point let us say C, this point let us say B. Its flexural rigidity EI value is infinity, this length is say L. This is simply flexural rigidity EI. That means very strong beam connected to weak beam. If EI is infinity, that means this member will not deflect. It remains as it is here only. That means this member behaves like a fixed support, because you fixed it here, it will not rotate. That means it remains horizontal. So now for this beam, if you are able to draw the deflection profile, that profile will give you some idea of how we should manage to find moment at B. Now you see, this is our problem. You go and apply some moment M. This M is applied. Applied moment, this point is a C, L and L. Then at this point C, we know slope must be 0, beam cannot deflect. Cannot deflect, slope is also 0. If at all it bends, only AC member should deflect. like this. So slope is 0 here. So this is A is infinity. Because of that it remains straight line. So curve must be smooth curve. Like this it will go. Now you see, this profile we know how to manage. This behaves like a fixed support. You have now AC beam, one end fixed, one end hinge. You applied a moment M. We know how much is the carryover moment here. So cut here, throw it out. First deal with this one. Okay. So this one now will behave like this. Because this profile we can manage. This is almost behaving like a fixed support. A, C, L. You are applying a moment M. How much moment will develop here? Clockwise only. M by 2. Total 1.5 M clockwise. So anti-clockwise. VC you will get 1.5 M by L. Okay. MC is M by 2. Then who will give this VC and MC to the beam AC? These two forces are exerted by CB member on CA member. That means in return, on this member, if I draw this free body diagram, see this will not go down. It will remain here only. No deflection on this one. But VC is acting vertically down. This force is 1.5 M by L. If this is clockwise, here it should be anti-clockwise. How much? M by 2. This may not deflect, but it is in equilibrium. So what is the reaction here? It's like a cantilever. You don't have to worry about the deflection. 1.5 M by L down. So here VB is 1.5 M by L up. Next moment. So what is the bend moment at B? 1.5 M by L into L anticlockwise plus 0.5 M. So total moment is 2 M. So to balance it clockwise, MB has to be 2 M. See 1.5 M by L into L. Anticlockwise moment how much? 1.5 M. This is anticlockwise. 0.5 M. So total anticlockwise moment is 2 M. Clockwise is 2 M. So this member is completely in equilibrium. This 2 M, the reason for 2 M is M. That's why this is called COM. So carryover factor CAB is equal to carryover moment at B by applied moment at A. So you will get 2M by M. So carryover moment can be more than applied moment. As I told you, some cases your applied load is different, reaction can be more than that. So depending on the configuration of the structure, the moments can be more than the applied moments or reactions can be more than applied loads, as we have seen in the overhang cases. So this is extreme. If EA is infinity, you will get 2M. Reverse case you take it. This is compared to this one, this is very strong. Then limiting case is infinity only, so 2M you got. Now CB member, I will keep same EI. Then what will happen? We know 2M becomes M. Now instead of EI will reduce further. Then fixed end moment required to fix it will further reduce to less than M by 2. That means carryover factor can be less than 0.5. Let us see now one more example. Once prelims they have asked that question. This is 2EI, this is EI. That means this portion they have reduced, size they reduced. Then moment required to fix it is less than M by 2. As you have seen in this case, if it is more stiffer, more effort is required to make the slope 0, 2M is required. Otherwise less effort. Okay. Now let us see that question. Now, if you reduce this one, the stiffness, the carryover factor will be, carryover moment will be less than m by 2. This I remove now. Carryover factor CAB is, now see, we will make here a strong member, then weak member, fix it. Earlier problem it was infinity, now it is less. This point let us say A, B, C, length is L, L. This is say 2 EI, this is say EI. Option is exact value. If you want to calculate, it takes 3 minutes time, because earlier I have given you carryover moment is m by 2. You have done moment area method. I have drawn the bend moment diagrams, individual bend moment diagrams. Then you have calculated. If I values are different, then what will happen is the triangular area you have to take separately. So calculation intensive only. So that's why they asked you only to guess. Will it be more than 0.5 or less than 0.5? So option A is 0.5. B is less than 0.5, greater than 0.5, none. Like this they give. Now you see, in this case, this is the one. You apply M. This point say A, C, B. Because this I value is very less, to fix it also effort is required is very less. You don't have to apply more effort. So MB value now is less than M by 2 COM. So now carryover factor is less than M by 2 by M. So you will get carryover factor is less than 0.5. So less than 0.5. If you add reverse direction, supposing that like this you are adding, if it is infinity it is 2m, but not infinity, I values are different, EI to EI. CAB. Now in this case when you apply moment M, limiting value is 2m, because if it is infinity. If it is less than, if it is same, 0.5. If it is infinity, this half you will get 2m. In this case now it will be how much? MB. At least we can say it is greater than m by 2. Whether it is 2m or not we cannot tell, but greater than m by 2. This value is greater than m by 2. So carryover factor CAB is greater than m by 2 by m. So you will get greater than 0.5. If it is a 20 marks question, then you have to draw the bend moment diagram. A by A you have to write. Then fixed end moment I have told you theta B is equal to 0. So from that compatibility condition, you will know what is the moment at B required. Okay, that is a process. 20 marks questions they will ask in the exam. So this is about the carryover factors. If it is infinity, you don't have to manage this bend moment, the deflection profiles we know how to manage. So easy for us to get it. Now the third concept I gave you was stiffness factor. Let us see how questions come on the stiffness factor. on the third concept, things will go like this. Moment required at B to produce unit slope at B is, assume that we have a continuous beam. How much moment M you have to apply so that theta B becomes 1? This is 4 meters, 3 meters. I value, let us say, same. How much moment M you have to apply so that theta B becomes 1? Then for that what we do is, first you draw the deflection profile. That will give you some idea of how we should manage the problem. When you are applying a moment M, when you turn it like this, the deflection profile is something like this. Now we wanted this theta B to be 1. Because ABC is a continuous beam, when you are applying moment, both segments will bend. Okay? Now, forget about this M and this part. Deal with this deflection profile alone. For this profile, when far end is hinged, how much moment you have to apply so that theta becomes 1? When far end is hinged, 3a by L. So keep that. So whether it is, if it is there, fine. If it is there or not, for this profile to happen, on this alone I have to apply 3ei by L. Then theta b becomes 1. Then for this one to happen, again clockwise only I have to rotate. When far end is fixed, now cut here, throw this piece out. I have to apply 4ei by L. But both beams I have to bend with the help of M. So 3ei by L for this one, 4ei by L for this one. So total amount of that 7ei by L, if you apply like this, that moment will be shared by both the members, 3ei by L, 4ei by L, and theta becomes 1. So moment at B. For this one, for this profile, that's why I told you, if you know the profile, deflection profile, if it is a known profile, simply you have to attach the moment and slopes. This is 3ei by L for the span BC, and for this one, 4ei by L for the span BA. Okay, so you will get 3ei by 3 plus 4ei by 4, because spans are like that. This is 3 meters, this is 4 meters. So you will get 2ei kilonewton meter. If you, one of the options will be this. If you apply 2ei kilonewton meter, theta b becomes 1. This is one way. Another way is they give you moment. They will ask you to find slope. Slope at B is, assume that you are applying a moment of say 40 kilonewton meter. This point, let us say A, B, C. Same problem I am giving. In one paper they asked this also fixed one. M they have given some 40 or 50. What is theta B? So this is 3 meters, 4 meters I. Now 40 kilonewton meter. For theta B to become 1, you know how much moment to be applied. Then for 40, how much is the rotation? Linear interpolation. For theta B to be 1, M is equal to, for this span 3ei by 3, for this span 4ei by 4. So 2ei kilonewton meter. So for M is equal to 2ei kilonewton meter, theta B is equal to 1. For M is equal to 40 kilonewton meter, theta be how much? 40 by 2 EI. So you will get 20 by EI radian. Like that. Means where time is very less. Actually slope deflection method, moment distribution or matrix methods, we can use them, but that much time you don't have to spend in the exam. Simply also we can manage. The questions they give you, they are such that some thinking process is required where quickly you can manage the problems. Okay. Now, last concept I gave you was the distribution factor. On distribution factors, how the equations can be given. Moment at A is this, there is an applied load of say W. This point say A, B, C, D and E. All lengths are same, flexural rigidity is same. What is the moment at A? Now you see, for this what we do is, first we will remove the overhang. That means even in moment distribution method also when you are dealing with that, overhangs we remove them. Because in the overhang, axial force, shear force, bending moment, everything is known. What is the shear force here? W. Axial force 0. Bending moment is W into X. So everything is known to us, so there is nothing for us to analyze. So cut, throw it out. What it does on this one we show, and you analyze this structure like that. So now this is now equivalent to this one. The effect of load A, B, C, D. Effect of load at C is one load W. This directly acts on the column W and a clockwise movement of M, W into L. This W acting at C, this BCD will share no part of W goes to AC because it is direct transfer to the column. But this moment M, whatever you apply, in the ratio of their distribution factors, they will share. Because all members are equally strong, Li, 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 and conditions are same, your applied moment gets shared or gets distributed to all members equally. So the share is equal. So if I see this one, this point let us say A, B, C, D. Now out of M, this fellow will take same direction, M by 3. This will take M by 3. This will also take M by 3. In this ratio, it gets distributed. Once AC member share is known to AC fellow, I can cut this, throw this piece out. Cut, throw that piece out. Don't deflect C. Keep C as it is. M by 3 only moment is it is taking. So once moment, how much it takes is known, the deflection profile is like this for AC alone. This also will deflect, but we are not interested in that. So wherever you have this deflection profile, if the C doesn't deflect, far end is fixed, carry over moment is m by 2. So total m half will not share. Out of total m, it's this fellow at C is taking only m by 3. Whatever it takes at C, it's a share. Out of that, half will be carried over. Not whatever moment you apply. If you apply 1000 ton meter, say, this fellow has taken 900 ton meter, this fellow has taken 50 ton meter, this fellow took only 50. Then only 25 is transferred. 1000 by 2, 500 it cannot take. Because here itself is only 50 and here it cannot be 500, like that. Okay. So here your MA is nothing but half of the applied moment. So m by 3 by 2, that means m by 6. M means WL by 6 clockwise. So in 2 minutes time, this is your task. If they want to ask you slightly tougher question, they can ask you like this. What is slope at C? For this profile, I told you to remember also ML by 4EI formula, where M is M by 3, length is L, ML by 4EI. So like that we should get it. See here, note 1. Theta C is equal to m by 3 into L by 4EI, where m means WL by 3 by 4EI. So if they ask you slope at C, WL square by 12EI, you have to answer. Then if you see the deflection profile, not only one member, all three members will deflect. By the same slope, because they are rigid, that is a rigid joint A, B, C, D. See here, if it deflects like this, then this has to deflect like this. This is the deflection profile. Supposing that, now third point, how W gets shared, if you want to know, this is what will happen. Only W we are drawing. This point say B, C, D. At C there is, I told you, the W direct transfer. This length is L, this length is L, area is same. Now this becomes strength of materials problem. When I am pulling it down, this will, the reaction here, when I am pulling it down, the reaction at B is VB upward, and here when is pulling it, pushing it down, VD is upward. Now in what ratio both will get distributed? If you know the axial stiffness, that's what strength of materials also have taken. If axial stiffness of two members are same, the share of your applied load is also equal. So W by 2, W by 2. If this axial rigidity or axial stiffness is 4 times than this one, its share also 4 times than this one. Like that. Since it is equal, VB you will get W by 2. VD is also W by 2. And that means if you take CD member is under compression, BC member is under tension. Now you see, this is the free body diagram. This is W by 2. This is also W by 2. This member is B, C. Next free body is like this. See, this W by 2 is the action. So if it is downwards or upward, we should not put it. Your W is shared by these two members like this. Half this fellow has taken, the remaining half this fellow will take like this. W by 2, W by 2. Now these two free body diagrams, if you shunt them, W by 2 plus W by 2 is W, it will match with this one. Similar to your earlier problem I told you. Whether it is strength of materials or structures part of it, applied load is there, so then it will be shared. How they will share depends on either axial stiffness or flexural stiffness. This is your strength of materials first chapter problems we have done like this. But here the elongations, contractions are neglected in the moment distribution method. Okay, so that is an assumption. Axial deformations, shear deformations are neglected in moment distribution method. Then clockwise rotations, clockwise end moments, we take them positive. Anti-clockwise rotation, anti-clockwise and the end moment, we take them as negative. That anti-clockwise, negative, clockwise, positive, you will do only when you are distributing the end moments. But when you are drawing the bending moment diagrams, then sagging positive, hogging negative only we have to take. Okay. So this is the basis for the moment distribution method and corresponding assumptions. Sagging bending moment positive, hogging bending moment negative. Clockwise rotations, anti-clockwise, clockwise rotation, clockwise moments positive. Anti-clockwise rotation, anti-clockwise moment negative. When we say clockwise, anti-clockwise means you are not worried about the bending moments. Then simply moment M you apply, same direction if it is transferred, positive, opposite, minus. Whether it sags or hogs, we will not worry. Okay, such issues, the moment is the assumptions and how BMD should be drawn. Now we'll take the next concept. Sign conventions. Sign conventions in moment distribution method. We take the clockwise end movements, clockwise rotations, we take them as positive. Anti-clockwise end movements, anti-clockwise rotations are taken as negative. This clockwise positive, anti-clockwise negative, we use this sign convention only when you are distributing the end moments, not when you are drawing the bending moment diagram. End moment distribution means the external effects we are transferring. That's all. So only such cases clockwise positive, anti-clockwise negative. Okay. So clockwise end moments and clockwise rotations are taken as positive. Then anti-clockwise end moments anti-clockwise end moments and anti-clockwise rotations are taken as negative. This sign convention is used while distributing end moments only. While distributing end moments only means, last classes I told you, at one end you apply say M. As a reaction, how much is carried over is M by 2. So that has again same sign. Then we have taken distribution factors. When you apply clockwise movement, how that movement gets distributed. So there also that distribution we take it as, if it is clockwise positive, anti-clockwise negative. In that we don't see whether the beam is sagging or hogging because of the movement. Okay. Then sagging bending moment positive, hogging bending moment negative. When you will take that sign convention you will use only when drawing the bending moment diagrams and nowhere else. Okay. Second point is sagging bending moment is taken as positive. Hogging bending moment is taken as negative. This sign convention is used while drawing Bend-Newman diagrams only. This is for Bend-Newman diagram, this is for distributing end moments only. Okay. Now, one more assumption we make, that is the effect of axial force, the effect of shear force. That means the axial deformation, shear deformation we neglect in our slope deflection method and also moment distribution method. Okay. So, this axial force, effect of axial force means strength of materials you have studied on this member. If you apply a force P, let us say, then axial deformation is PL by AE. In the frames or in the beams or where they are primarily subjected to bending moment, axial forces sometimes they will be 0 or very little amount of axial force only will be there. So small the axial force that PL by AE value can be rounded up to 0. And also shear. Shear force are in your strength of materials you have studied about the bending moment. Due to transverse load, the cross section is subjected to shear force as well as bending moment. Due to that shear force diagrams you have drawn, bending moment diagrams you have drawn. Because of the bending moment, you found the deflections, you found the bending stresses. Due to shear force, shear stresses will develop. Shear deflections, bending deflections will be there. Shear deflections also will be there. Due to shear, there is a deformation which produces additional deflection. That shear deflections also we neglect in our moment distribution method. Then that shear deflection or shear deformation, where you will consider in concrete, when you have a deep beam. In our steel structures, you will consider when the web is not solid. That means verandel trusses, lacing and means built up columns with lacing and battening. There the shear deflections or shear deformations you cannot neglect. Those special cases we will see in the design of steel structures. But here when you are analyzing it by moment distribution or slope deflection method or matrix methods, the shear deflections we neglect. Okay. So the effect of axial force and shear force, that is axial and shear deformations, axial and shear deformations are neglected. Are neglected in MDM. The effect of shear is so less if you have a solid I section is there, say. You are using beam as a solid I section. Then shear deformations are so less that you can round them up to 0. But Verandel trusses where you don't have a solid web. Depth of the beam will be around 3 meters or 4 meters. At intermediate locations only web will be there. Or if we take the lacing battened column, if it is subjected to movement, there is a space between the two components of the column. There what happens, if at all shear is acting, since there is no solid cross section, then shear deformation will come. So in the steel structures, in the design of lacing, design of battens, design of Verandel trusses, you have to consider the shear deformation. In concrete structures, deep beams, you have to consider the effect of shear deformation. In our in our BTech level, only these 3 applications where you have to consider shear deformations in addition to bending. No other place we consider the shear deformations. Even when you are finding kinematic indeterminacy also, shear deformations we round them off to 0. Okay. So with this understanding, now let us see what Hardy-Cross did in his moment distribution method. Now analyze the continuous beam. Continuous beam shown in figure using MDM. Analysis means finding axial force, shear force, bending moment. Design means you are given shear force and bending moment, you will fix the size of the beam. Fixing the size of the beam is called design. Once size of the beam is known, what is the shear force, what is the bending moment, finding those values is the analysis. Okay. So now we want to analyze the continuous beam. Now size of the beam is given to us. Assume that we have a continuous beam like this. This is subjected to UDL, and here there is a point load. This UDL, let us say 12 kilonewtons per meter, span is say 4 meters, A, B, C. This load, let us say 8 kilonewton, this is 2 meters, 4 meters, I. In the trusses, I told you indeterminate trusses, when you want to analyze the cross-sectional property, material property will also come into picture when you are finding the reactions or the moments. But in a statically determinate structure, the reactions, shear force or the bending moment are independent of cross section, independent of material property. But for indeterminate structures, continuous beam is now is indeterminate structure. So the shear force, bending moment, they depend on the I values. Okay. So material property, cross sectional property influence the support reactions, also the moments, as we have seen in the fixed beams. So I value beforehand we must know. Without knowing the cross section, you cannot analyze the indeterminate structures. So that's why beforehand itself I values. Then how to fix them? Then approximately we will fix some I value, then analyze it. Then if at all the whatever cross section, if it is not sufficient, then you have to modify the sizes of the beams and reanalyze them. So the indeterminate structures design is a trial and error procedure type. Okay. So that's why we assume now time being that I values are given to us because it is happens to be indeterminate structure. Now this space we use it for shear force and bending moment. Okay. Now your first step is as the moment distribution method. First what we do is we will find the fixed end moments. Fixed end moments means we will find the locking moments. What it means is first whether it is a fixed or hinged or roller, first you lock them. Locking the joints means that don't permit the slopes to happen. Why we should do that? If you don't permit the slope to happen means you know how to find the fixed end moments. When you release them, you know how much is carried over to the other end. So an unknown problem you convert into a known problem and analyze and finally find the what is the end moment in the beam segments. So first step is this one. Find fixed end moments. When you are finding the fixed end moments, this is the sign convention. Clockwise end moments are taken as positive. anti-clockwise end moments are taken as negative. Now span AB, in this case ABC is a single beam. Okay. So at B, single beam, it is simply supported at B. Actually there is no pin at B. AB and BC are not separate members. ABC is a single member. If at all there is no gap vertically, I told you roller can be kept here itself. If there is gap, let us say, then you two triangular plates you will weld it on two sides. Base plate you will weld it. Below the base plate rollers will be there. Those rollers will permit the free expansion or contraction due to temperature changes that happen due to sun shining. Okay. So clockwise end moments positive, anti-clockwise end moments negative. Actually these are not fixed supports. We symbolically find the fixed end moment. We symbolically fix the joints. So it's like this. This point A, B. This load is 12 kilonewtons per meter. For this one we know fixed end moment. M moment fixed at A for the span AB. Anti-clockwise, so minus WL square by 12. W means 12, L means 4, WL square by 12. You will get minus 16 kilonewton meter. This is MFBC. MFBA, fixed end moment at B for the span BA. Clockwise is there, so plus you have to write plus WL square by 12. You will get plus 16 kilonewton meter. Next, similarly BC span, you will fix it. There is a central point load 8 kilonewton. This is 2 meters. BC. This is fixed end moment fixed at B for the span BC. Anti-clockwise, so minus WL by 8. So minus WL by 8. So you will get minus 4 kilonewton meter. This is MFCB. You will get plus WL by 8. So you will get plus 4 kilonewton meter. Actually you see A, B, C are not fixed supports. Now you fixed them. It is a symbolic representation of locking the coordinates. Now it is simply a symbolic representation of fixing all the joints. Actually they are not fixed, but we don't know how to analyze. So symbolically we will fix them. Since they are not fixed, we will release them. Okay. So first we lock all the joints. Next, second step, find distribution factors. When you are finding the distribution factors, at A, when you lock this one, that means a symbolic representation of locking, but it is not actually fixed one. So at that support, fixed support, there is only one member. If at all at this joint only one member is there, second member is that bolt. So if at all you apply any moment, how many members will share? Pin says I cannot take it. So whatever moment you apply, only one member will take. So its a distribution factor at A is 1. That means at a joint, if there is only one member meeting, its distribution factor will be 1. At this point, if you lock them and you apply some moment, say, that moment will be distributed in the ratio of their distribution factors. So those distribution factors will find. So that is, when you unlock them, you have to unlock the joints. When you are unlocking them, you only have to unlock. So in the process, you have to apply some moment. So when you apply some moment, how it gets distributed, we are finding. So that is the distribution factors. This is the point. If there is only one member meeting at a joint, its distribution factor is 1. But otherwise, you have to find the distribution factors. In this case, at B, when you apply any moment, length of the member, I value, length of the member, I values are same. So distribution factors are whatever moment, if at all you apply, that moment will be shared by these two members equally. That means distribution factor is 0.5, 0.5. By inspection, you can find it. In the exam, questions will be given such that the distribution factors by inspection itself you can find. Otherwise, maybe 10-15 seconds you can get it. If you have to find by inspection, if you could not find, this is the process. Joint, member, K, sigma K, and distribution factor is K by sigma K. Now you have to consider only joint B, because at A there is only one member AB, distribution factor is 1. At C also there is only one member, since you lock it and when you apply moment only one member has to take it. So distribution factor at C is also 1. Next, but for member at joint B, two members are meeting, BA and BC. So BA, BC, two members are meeting. When you are applying moment at B, then that moment its stiffness factor or relative stiffness, I told you distribution factor means K by sigma K. So when far end is hinged, wherever you are applying moment, that is a near end. The other end is far end. So at joint B, when you are finding the distribution factors, you are at B and you are applying some moment at B. Now far end is hinge here, far end is roller. Hinge and roller almost behave similar way. So when far end is hinged, we know the relative stiffness 3 by 4 I by L. This is also 3 by 4 I by L. L here is 4 meters. Summation is, now how much you will get? 2 times 3 by 4 I by L. 1 plus 1. So this by this means 1 by 2. 0.5, 0.5. So in this case, by inspection we can find it. If not, this type of table we have to write. So distribution factors we found. Now the end moments means which end moment? These fixed end moments we have to distribute. Minus 16, plus 16, minus 4, plus 4 are the fixed end moments. Those moments we have to distribute. Now this part I'll remove, I'll start here. I'll split into 3 parts. Now your third step is end moment distribution. Always moment distribution means either fixed end moment distribution or any applied end moment distribution only. Okay, for this end moment distribution, we write like this. Joint these three will show like this: A, B, and C. Then distribution factors you will write here. At A for the member AB it is 1. At B for the member BA it is 0.5. At B for the member BC again 0.5. Then at C for the member CB is 1. Then fixed end moments. Here just now we have calculated MFAB is minus 16, MFBA is plus 16, MFBC is minus 4, MFCB is plus 4. So these fixed end moments we have to write like this. What this means is, what this line represents is like this. At A, for the member AB, if I want to fix it or if I want to lock it, I have to apply minus 16 kilonewton meter. Next, at B for the member BA, if I want to fix BA alone, I have to apply plus 16 kilonewton meter. Now at B for the member BC, if I want to fix it, I have to apply minus 4 kilonewton meter. At C, I have to apply plus 4 kilonewton meter. Then all joints will get fixed. Now this is plus 16 minus 4. If I want to completely lock the joint B, I have to apply a net moment of 16 minus 4 means plus 12. If you apply plus 12, both members get locked. Means both members slope is 0. Locking the joints means making the slopes 0 so that slopes are not permitted. Now this is fixed end moments means moments necessary to lock all the joints. Now come to the actual problem. First treat the end joint so that our process will be quickly completed. A and C are not fixed, but you have unnecessarily fixed them. Why we fixed? Only then we know how to find it. Now we know how to release also. You fixed it unnecessarily, now you release it. Releasing joint A means you apply plus 16. Then whatever moment you applied, you have removed it. That process of unlocking is called releasing. Release A and C. This is minus 16 to fix it. Now release. That means plus 16 you apply. Here plus 4 is to fix it. Now release this one, minus 4. Now you see, they are not fixed supports. They are only at A fixed support we have shown, but actually fixed support is not there. It is only a symbolic representation of fixing the or locking the joints. But now you unlock the joint. So plus 16 you applied. Release A and C means who will release? We only have to release. That means on the locked joint, you went and applied plus 16. The B joint also is a locked one. Unnecessarily we locked it. So because it is a locked one, out of plus 16, how much is carried over? Because B is now a fixed support, means a locked one. You locked them. Then carry over moment, how much is carried over? Out of plus 16, because it is now a fixed one, plus 8 will be transferred. We know that when far end is fixed, half the moment is carried over and in the same direction. So minus 4 again, minus 2 will be carried over. Okay, now this point we can remove. These are called carryover moments. Whatever first concept we have learnt, that carryover moment whatever we have learnt, that we are writing those things instead of writing separately in a tabular form we are calculating. Now when you carryover moment comes like half the moment is carried over, now we can calculate. Now net fixed end moments we can calculate. Net fixed end moments. Here it is 0. At A fixed end moment should be 0 because not fixed at all. Now 16 plus 8 plus 24 minus 6. This is 0. At C now 0 moment should be there because you released the lock. So A and C. B you didn't release. Lock as it is locking to only is there. In the process now to lock joint B you have to plus 24 minus 6 means there is a plus 18 kilonewton meter. Why plus 18 was there? Because it's a locked one. So there now exists still plus 18 kilonewton meter. But B is also not a locked joint. That means B is also not a fixed one. So now all intermediate joints you release them. So that is called release. we also call balance. Release or balance B now. Supposing that intermediate supports 3, 4 are there, all 3, 4 we have to balance or you have to release. Now you see, when you come here, there is now how much net fixed end moment is plus 18. 24 minus 6 plus 18 is there. Plus 18 is to fix it. Now you have to unlock it. To unlock it, you only have to go and apply minus 18. When you apply here at B minus 18, how it gets distributed? It gets distributed in the ratio of their distribution factors. This is plus 18 means now you have to apply minus 18, then it becomes 0, means it's completely unlocked. Since you applied minus 18, it gets distributed 18 into 0.5, so minus 9. So here minus 9, here also minus 9. So minus 18 you applied to unlock it, that gets distributed. Two members will take minus 9, minus 9. So when you apply minus 9 here anti-clockwise, how much of this is carried over here? Carry over moment, because this is what you applied, it got distributed. Because of this moment, carry over moment here is 0. When far end is hinged, carry over moment is 0. First concept I told you. Here also carry over moment 0. So carry over moment, carry over factors we have made use of here. Okay. So whatever first 5 concepts we have learned, we are writing now in the form of a table. That's all. After carry, you fixed them, you unlocked them, problem is over. That is called end moment distribution. So when you unlock them, it gets distributed in the ratio of their distribution factors, problem is complete. In the exam, not more than this you will be asked to do, because you have only 2 minutes time, and only one time when you balance them, there will be nothing for us to do anything. After this one, if at all 20 marks questions are there, then ABC it will not stop, A, B, C, D, E, like that will be there. Then at least 3 times you have to balance, because 20 marks means 5, 6 minutes. So at least 3 times we balance it and stop the work. So unlocking, relocking, we have to do it. So in these cases, in the prelims exam, or whether you take civil services or GATE or engineering services, any objective questions type examinations, the task will be only this much. Okay. So after this, now you will get final end moments. Final end moments. Here it should be 0. Only this part you have to add. 24 minus 9, you will get plus 15, minus 15, 0. Now you see, what is the net fixed end moment at B is 0 only. At this point plus 15, BC minus 15. So now joint equilibrium satisfied. Here plus 16 minus 4 not satisfied. So one side plus 16, one side minus 4. These are the moments necessary to fix them. These are final end moments after the beam rotates. First you locked them unnecessarily, so all slopes are 0. To make the slopes 0, plus 16 minus 4 is required. But slope at B is not 0. So when you unlock it, the moments get adjusted. Finally, they settle down at both the joint B rotates. After rotation, then the final end moments will be plus 15 minus 15. Because of the continuity of the beam over the support at B, there will develop end moments. Hogging bend moment will develop. Only one moment. At one point, one moment only possible, whether you see left side or right side. So that's why plus 15 minus 15 they should match. Then it means that that joint is in equilibrium after rotating. This is before rotating fixed end moments. After the joint rotates, they settle at plus 15 minus 15 and they stay in equilibrium. This process we call it as end moment distribution. Okay, this I'll write as a process what we have done. First, that release A and C means we will write. So meaning of that we'll write. This is the releasing A and C means unlocking the joints A and C. Unlocking the joints A and C. Next, second point. Entire process will write it. Okay. This end moment distribution, your first task is fixing the all joints except free end. Free end, what happens when far end is free? That means it behaves like a cantilever beam. In the cantilever beams, axial force, shear force, bend moment, everything is known to us. We don't have to unnecessarily fix it and release and waste our time. So, except free end, all other joints you have to fix them, lock them, and find the fixed end moments. That is the first step. Okay. So, in this entire process, I am writing in end moment distribution, we fix or lock all the joints. Lock all the joints except free end. And fixed end moments are calculated. And fixed end moments are calculated. Now, after this, if at all end joints are hinged A and C like this, you have to release them by applying moments opposite to that, and carry over moments you have to calculate. If end joints are hinged, then release those locks. Release those locks by applying moments opposite to fixed end moments. Moments opposite to fixed end moments. That means this one. Releasing by applying moments opposite to fixed end moments. Opposite to fixed end moments, and net fixed end moments are calculated. Net fixed end moments are calculated. After this, we release all intermediate joints also. First end joints, then intermediate joints. Release the locks of all intermediate joints also. This process is called releasing or balancing. Releasing or balancing. Now, this procedure you have to repeat. In this case, after releasing it, problem was over. If it is a 20 marks question, some here also continuity is there, say -9, some more continuity is there. Half is carried over, -4.5, then distribute it, then lock it, then distribute it, then lock it, like that. Then that process you have to do it at least 2 or 3 times. Full stop. Repeat the same procedure. This repeating the same procedure is for 20 marks question. 2 marks question means this repetition will not come. So that means such a long question they cannot ask in 2 minutes time. Repeat the same procedure till no locking moments are developed. Till no locking moments are developed at any intermediate joint. That means when you half the moment when you carry it over, it will be so small that there is no need to lock the joint at all. Completely joint will be unlocked. That means carry over moment you get say 0.01 kilonewton meter. That means there is almost no moment at all. That means no fixed at all developed. So no fixed end moment is developed or no locking moment is developed. That means the joint at that joint members are completely rotated and they are staying in equilibrium condition. Complete till the zero means almost zero value we don't release them. That means in the textbooks on the workbooks you will find that carry over balance like that 6 to 7 times they have done. 6 to 7 times if you do it, for that question only 20 marks question, let us say you may get to 20 marks, but other places because time you have spent around 15 minutes time, other place 60 marks you will lose. So you only should tell them that how the end moment distribution is carried out. You must show them only 2 times or 3 times only and close the values and write the final end moments. Question of doing third time or fourth time should never come. You should only tell them that how it can be done. Okay, if at all they want to cut 1 mark, say out of 20 marks you get 19 marks say, but you have lot of time still with you, other problems you can solve effectively, completely. So this is the process. For 2 marks process things I am telling now. 20 marks questions when you have to repeat the procedure. Then when you come for mains, again we will discuss there how we should repeat at least only 2 times or 3 times. Okay. So till no locking moments are developed at any intermediate joint. So this is the process of end moment distribution. Okay. See that first we'll fix or lock them. Unnecessarily fixed, then release them. First end joints have to release. Once you went and released, half the movement is carried over to all intermediate joints. Then what are now at this position, what are the net fixed end moments? In the process, intermediate joints you didn't unlock. Now that process you will do now. All intermediate joints you have to release. To fix it, you require plus 18. Now release it. Minus 18. When you apply minus 18, that minus 18 will be distributed to two members in the ratio of their distribution factors. Minus 9, minus 9. Since minus 9 you applied, half of that is carried over here. But here A is now completely unlocked, hinge support. So from here to here, no movement will come. Because when far end is hinged, carry over movement is 0. Otherwise, half of that movement we could have carried out if it is a fixed support. That example we'll take in the next problem. Here also from here to here 0. Then problem is over. You unnecessarily locked them, you unlocked all the joints, issue closed. Then what are all the final end moments? That is the end moment distribution. Okay. So after finding the final end moments 0, plus 15, minus 15, 0, now you must find what are the support reactions. That we will do in the fourth step. This part I remove. Fourth step is support reactions. These support reactions, again, With the help of free body diagrams, we must do it. Even if you make a mistake, correction also becomes very simple. What we do is free body diagram means this is AB, BC spans. Free body diagram of AB, free body diagram of BC separately you draw. On the free body diagram of AB, UDL is there, point load is there. Show applied loads. In addition to the applied loads, end moments also will develop because of the supports. Show them. Now free body diagram is complete. Then because of the load, what are the reactions? Because of the end moments, what are the reactions? Add them. How can you add? From the principle of superposition. So use principle of superposition to find the final reactions. So from now onwards, you must always do like this only. See here two members. This is one member. This is second member. Okay. This is A, B, B, C. On this UDL is there, show that. This is 12 kilonewtons per meter. This is called free body diagram. Free body diagram means it is the diagram of a body on which what others are doing you have to show. So what applied load is doing you have shown. This is the free body diagram. Then moments. See here at A, for the member AB moment is 0. 0 means you can show clockwise or anti-clockwise, our choice. Then at B, this is BA span. At B, for the member BA plus 15. Plus 15 means it is clockwise end moment. So you must show plus 15 kilonewton meter. Because it is plus, you have written clockwise. Now at B, for the member BC minus 15. So you must show minus 15 means anti-clockwise, like this. Minus 15. Now here 0. Like this, applied loads, end moments. End moments which you have got from the end moment distribution, you must show them. These are plus 15 and minus 15 are not fixed end moments. Those fixed end moments got distributed and settled at these values, and at this magnitude the beam after rotating it is completely in equilibrium. Now the principle of superposition. See here at the center of AB you draw one line, center of BC you draw another line, end of C draw one line, left of A you draw one line. Now you will get a box like this. This box is for the reaction at A. This box is reaction at B. This box is for the reaction at C. Now you see what we have done was, first point is due to applied loads. Reactions due to applied loads. Now you see this AB beam now is like a simply supported beam. A simply supported beam, this is support at A, this is support at B. On this simply supported beam there is UDL. Next, on the simply supported beam there is a moment of 15. Due to loads alone, what are the reactions? Due to moments alone, what are the reactions? Add them. So 12 into 4, 48 kilonewton down. To balance that, two supports will exert 24 here, 24 here. So 24 kilonewton upward, here also 24 kilonewton upward. Like a simply supported beam subjected to UDL means both will share equally. This is support A, this is support B. Similarly here, this is also support B only. Coming, that means on the support B, 8 kilonewton load will produce some reaction. This UDL produces some reaction. So principle of superposition. So due to 8, we know here 4 kilonewton upward, 4 kilonewton upward. So these are the reactions due to applied loads. Next, reactions due to end moments. reactions due to end moments. Now see, strength of materials you have studied in a simply supported beam. If there is a moment M say, then anti-clockwise couple will develop M by L as the reaction. Couple will develop. Here 0, here 15, 15 clockwise. To balance clockwise moment, M by L anti-clockwise. So M by L anti-clockwise means see how my fingers are moving down, up. This is anti-clockwise. So here reaction should go down, here it should go up. Formula is M by L, 15 by 4. You will get around 3.75. This is nothing but this one only. Supposing that if you have, say, a simply supported beam, you apply some moment M say. What is the reaction here? M by L, M by L. So whatever you have learnt in SM, we should not write a separate free body diagram and calculate reaction M is there and then M by L, sigma M0, then M by L is the reaction, should not be done. Because we have done already that when there is a clockwise movement M, M by L is the reaction. How the fingers moving anti-clockwise means down, up. So down, up. M by L, M by L. So here also 3.75 kilonewton upward. Coming to this one. On the beam BC, there is a moment of 15 anti-clockwise. To balance anti-clockwise movement, you must, these two supports will produce a clockwise couple. So move your fingers clockwise up, down. Here upward, here downward. 15 by L means again same value, 3.75 kilonewton upward, 3.75 kilonewton downward. Now this is due to support due to end moments. Now due to loads due to end moments. Now you can find final reactions. Since it is a linear elastic structure, principle of superposition you can apply. 24 up, 3.75 down. So you will get 20.25 kilonewton up. This reaction is VA. Then VB is because of these four, UDL as well as point load, and also due to clockwise 15, anti-clockwise 15 reactions will develop. So these are four reactions, you see all of them are upward. So add them. 24 plus 4, 28 plus 6, 34 plus 1.5, 35.5 kilonewton upward. This box is for VB. This box is for VC. 4 up, 3.75 down. So you will get 0.25 kilonewton upward. This reaction is VC. So in any continuous beam, whether you use slope deflection method, moment distribution method or matrix methods, if you are asked to find the reactions, you must be able to draw this type of free body diagrams. We use such free body diagrams everywhere, whether you take plastic analysis in steel structures or SDM, slope deflection method, moment distribution method or matrix methods. We have to use whether you take beam or frame. We must draw individual free body diagrams, what individual loads, individual effects you will find, reactions, then add them from the principle of superposition. Now these reactions will show here. VA we got it as 20.25, then VB we got it as 35.5, then you got VC as 0.25 kilonewton. Now you are ready for SFD and BMD. This we can remove. We do not require this end moment distribution. Now your fifth step is shear force diagram and bend moment diagram. If time permits, if they ask you deflection profile also, we can draw approximate deflection profile. For the shear force diagram, section left side upward or right side downward, you will take it as positive shear force. Left side downward or right side upward is negative shear force. This is, I told you earlier, they are deformation sign conventions. When positive shear is there, the deformation I have shown you, without the faces will remain parallel, only the longitudinal axis they rotate, that's all. So that is the deflection profile. That means there will be, due to shear deflections will be there. So those shear deflections, like bending deflections, shear deflections we neglect, but deflections due to bending moment we will consider. That's what you have learned in Macaulay's method of double integration, strain energy method, and then moment area method. Due to those, in those methods, you calculated deflections due to bending moment only. Due to shear also deflections will come, which you have conveniently neglected, because those shear deflections magnitude is very less. That magnitude will be more, and also effect also will be more if you have a deep beam or web is not solid. Then intermediate locations, web only connected, two flanges are connected at only intermediate locations, say, then in between gaps are there. Such cases shear also we will consider. Now this is a positive shear force. Now you see, as in the SM, as in strength of materials, you might have studied, shear force means shear force at LHS of C, RHS of C, all that statements you have written. Such statements you cannot write once you come to structural analysis level. By inspection itself, you must complete SFD. In the conventional papers, you will get 1 mark or 2 marks. So maximum of 1 minute, you must complete the SFD. Even in strength of materials 10 marks questions also, symbolically one example, shear force at LHS of C, so much, that's all. You show that, remaining entire diagram you draw, still they have to give you full marks. Okay. Now you see, for this diagram, okay. Now shear force diagram we want to show. Shear force at RHS of C means here. RHS of C there is no shear force, because at RHS of C there is no beam at all. So it cannot shear anyone. So this will produce no shear force in air. So we don't calculate. At C shear force is not defined. Means shear force is indeterminate exactly under point load. So you have to stand at LHS of C. You stand at LHS of C. Now you have the option of looking left side or right side. If I look left side, I have to deal with 1, 2, 3, 4 forces. But if I look right side, only one load. Easily I can manage. Section right side upward. You see, section right side upward is negative. So minus 0.25. Put below reference line. Now you travel like this. When you are moving like this up to here, up to RHS of that point load, no additional load came. Same load you are able to see. That means this should not change its magnitude. It should go like this. Okay. Same 0.25. At 8 you cannot calculate. Now cross the load, stop there. Suddenly there appeared a point load of 8 kilonewton. Deal with that. Section right side downward 8. Section right side downward is positive plus 8 minus 0.25 already was existing. So you will get 7.75. show that. Now travel like this. Is there any change? No change. And this will go up to like this, same value this way. This is positive. This is also 7.75. Now cross the load, point load, upward reaction, 35.5. Suddenly there appeared this load, stop there, manage. Section right side upward, this much. That means minus 35 plus 7.75, you will get 27.75. When UDL is there, at till the end of UDL you have to travel and stop here only. When you move right side, left side of A, we will fall down. So at RHS of A, okay. Now we stand at RHS of A and look left. Section left side upward 20.25. So positive. So 20.25 you mark it like this. Now from here to here you must draw a straight line, linearly varying line. Now that will not intersect at center. Why? This is only 20, this is 27. So it will not cut at center, somewhere here it will cut like this. Okay, somewhere here it will cut. This is the center point, this is here. This is plus, this is minus. This is 27.75. This is plus, this is minus. So this is your shear force diagram. Next, bend moment diagram. Sagging bend moment positive, hogging bend moment you will take it as negative. Now you see, when you are drawing the bend moment diagram, you will draw a reference line like this first. Bend moment diagram due to UDL, bend moment diagram due to end moment. Separately you draw two bend moment diagrams, overlap them. The area that gets overlapped, you cancel it out. The area that didn't get overlap is your net bend moment diagram. You should not calculate where the point of counterflexure happens, what's the magnitude of positive bend moment. They are preliminary, means strength of materials they are over. Now you have to show only a qualitative bend moment diagram. So first due to this is the loading here, when you come to this point, this is, let us say, you have a simply supported beam subjected to UDL. Okay. You know simply supported beam due to UDL, WL square by 8, 12 into 4 square by 8 means 24. That first parabola you draw. Then this is 0, this is hogging. Hogging moment, this 15 will give you hogging moment. First let us draw due to UDL alone. So this is the center point, as I have told you. Bend moment diagram will go something like this. We will draw a slightly bigger one. This value you get it as 24 kilonewton meter. This is due to UDL alone. 24 is at center. Next, due to this blue color one end is 0, one end is 15. To know whether this 15 produces sagging bend moment or hogging bend moment, this end moment you have written plus 15. Plus 15 there implies simply clockwise over. Now you are drawing the bend moment diagram. If I stand here, look right side, section right side clockwise, it will hogging bend moment. That means minus 15 you will get. Supposing that if I stand here, section left side clockwise, it will sag. If I stand here, it is looking like a hogging movement, but if I stand here, it looks like a sagging bending movement. Then shall we write it as sagging or hogging? How to resolve the issue? See here, if I stand here, safely I can stand here, section right side clockwise, it will hog. If I stand here, what will happen? We will fall down. Why? Because there is no beam at all. So when you are calculating the bending moment, you should not stand in air and try to calculate bending moment. It will not exist. There is no member to bend. I told you earlier the difference between movement and bending moment. So bending moment means you should be able to stand there, look one side. If you cannot stand there means you cannot find bending moment at that point. So bending moment in air will not exist. So you have to stand here only, hogging bending moment. This is minus 15, 0. Then bending moment due to end moments we know how to draw. See here it is 0, here it is 15, somewhere here it will come. Then when you draw the diagram, it will go something like this. This area got overlapped, so we should not show. This is cancels out. The area that didn't get overlap is this plus, this is minus. Now you see the net bending moment diagram is this one. This is positive quantity, this is negative quantity. Now, as you have learned in strength of materials, where is the maximum positive bending moment? Wherever shear force changes its sign, that means here. This magnitude is more than this one. This value is less compared to this one. This is maximum positive bending moment. You just write, that's all. How much its magnitude you don't have to show them, but symbolically at least you should write in the diagrams that wherever shear force changes its sign from positive to negative, at that location bending moment is maximum. We have studied. So you should simply show that. That's all. Magnitudes not required. Where the shear force changes its sign, also we don't have to show. But this you must show that maximum positive bending moment where it happens. Then they will understand that you understood how to draw the bending moment diagrams correctly. Next, this is 15. So bending moment diagram due to UDL, due to end moments you have drawn for the span BA. So it's complete bending moment diagram. Now independent of this one, you can draw another bending moment diagram here for the span BC. Now come to this point. If you take the span BC, it is now again like a simply supported beam subjected to central point load. Simply supported beam subjected to end moment. We know from strength of materials how to draw each bending moment diagram. So due to point load, triangle, another triangle due to 15, superimpose them, net bending moment you will get. Due to 8, what's the bending moment? WL by 8. This 24, how you get it is like this. WL square by 8, W is 12, WL square by 8. This is 24 kilonewton meter. Now due to point load, WL by 4, 8 into 4 by 4, you will get 8 kilonewton meter. So WL by 4 we know how to draw. For this span, 8 means somewhere here. First you show this one. If the end moment you see here, you cannot stand here look right side because section right side anti-clockwise we should not read it because you cannot stand in the air. So you must stand here. Section left side anti-clockwise. This is actually minus 15 as per the end moment sign convention. Bend moment sign convention, see section left side anti-clockwise will hog the beam. So minus 15 and here it is 0. Here 15 already have drawn. Here it is 0. So draw a straight line. So 15. Now this ordinate we know it has to be 7.5. Now due to point load it is WL by 8 means it is 8. Now draw this one. It will go like this. This ordinate is 8. Now net value we can find. The area that didn't get overlapped. This is didn't get overlapped. So minus. I can show in the perpendicular direction. Independent diagram this is 8. This is plus. Total is 8. This is 7.5. Then what is this small height? So 0.5 kilonewton meter. So net moment is only 0.5. This is plus. This is minus. This is your bend moment diagram. See, whatever we have studied in strength of materials, now everything matches. What you have learnt? If shear force changes its sign from positive to negative, at that location bend moment is maximum. So maximum happened. If shear force changes its sign from negative to positive, bending moment is minimum, means mathematical minimum. Minus 15. Minus 15 is minimum. When compared with, I told you mathematical minimum what it is in the influence line diagrams also. Once 0 is there, minus 15 is there, say. What is minimum? Not 0, minus 15 is minimum because it's lesser than 0. A beam can fail because of the minimum bending moment or maximum bending moment. That means because of minus 15 or plus this value, whatever it is, it can fail. Okay, same is the case in the principal stresses, more circles. When an element fails, it can fail because of the positive stress or negative stress. Positive means tensile stress, negative means compressive stress. Mathematically, if you see 0 stress, major principal stress is a 0, minor principal stress is a minus 20. Then with 0 it will not fail, it will fail because of minor stress, means minus 20 Newton per mm square it can fail. So it is not necessary that an element fails because of major stress. It can fail by minimum stress also, mathematical minimum value. Here also it is mathematical minimum. If shear force changes its sign from negative to positive, bending moment is minimum. Mathematical minimum is minus 15. Okay. Next, it changes its sign from positive to negative when you are moving along positive x-axis. Then bending moment at this point is maximum. So local maximum. Here in this is local maximum. This is also local maximum bending moment you will get. Out of these two maximum bending moments, which is absolute maximum bending moment if you want to find, you have to physically verify the magnitudes. Then you will know absolute means, then you will know what is the absolute maximum bending moment out of all those local maximum values. Okay, so everything tallied. Also you have studied if if bending moment is 0 at a section, if bending moment is 0, shear force at that section is what? Maximum or minimum? See here at this point, see positive to negative bending moment, well, this is called point of contraflexure. At point of contraflexure, this is the shear force. You see this value is neither maximum nor minimum. It will take some intermediate value because if m is 0, we cannot tell anything about V, means anything about shear force. That's what we have studied. Now those points we'll write here. So these observations we'll write now. See here, this is what we have learned. Note 1. If shear force changes its sign from positive to negative, bending moment is maximum. Bending moment is maximum at that section. From positive to negative, that is the case. Then bending moment is maximum. Second point, if shear force changes its sign from negative to positive, then bending moment is minimum. Negative to positive, bending moment is minimum. Bending moment is minimum at that section. Next, third point, if at all, if shear force is 0, at any section, then what is the bending moment? Then bending moment at that section is either minimum or maximum. It can be either minimum or maximum, if at all shear force is 0. Now, why it is like this? Not only the shear force bending moment curves, any mathematical curve it is the case. See here, this if I take it, 0 means bending moment is maximum. So, this what you have studied. For y to be maximum or minimum, dy by dx must be 0. Not necessarily bending moment curve, for any mathematical curve you take it, in that curve y ordinate to be maximum or minimum, dy by dx first differentiation must be 0. Okay, that is what you have studied. Similarly, here it is y in mathematics you have studied. In strength of materials, y is replaced by m. So, similarly for m, that means bending moment to be maximum or minimum, dm by dx, its first derivative must be 0. What is dm by dx? V. Dm by dx is equal to V is equal to 0. That is why if V is 0, then m is not necessarily maximum, it can be minimum also. Okay. So, we can say or m is V is 0, or we can say for m to be maximum or minimum, dm by dx V is 0 means dm by dx is constant. For m to be minimum or maximum, m should be constant. If m is constant, let us say dm by dx, ddx of some constant term is 0. We can say dm by dx is, shear force is 0. The meaning of this we can also write it as m is constant. If m is constant, dm by dx is 0. That means that will be a, we can say minimum or maximum. Okay. Next, if you want y to be maximum only, that fifth point I will write here. For y to be maximum only, what you have learned? Second derivative d square y by dx square must be negative. So, dy by dx first you have to find, again differentiate it. If that value is negative, then at that point you will get only y value maximum. Okay. Then similarly, for m to be maximum only, d square m by dx square, nothing but dv by dx should be negative. That means if dv by dx is negative, let us say, that means if it changes from positive to negative, then you will get maximum bend moment only. dv by dx is negative. That means that is if v changes from positive to negative, then m will be maximum, like that. Then you have studied for y to be minimum only, d square y by dx square must be positive. You should get a positive quantity. So, similarly, for m to be minimum only, d square m by dx square, which is nothing but dv by dx, must be a positive quantity. That means, if v changes from negative to positive, then m is minimum. You will get only minimum quantity. This what we have learned in mathematics, same thing is applied here also. No special cases as such here. Now, supposing that if they ask you, this I think we can remove. How the numericals come, let us see. Questions come like this. If shear force is 0 at a section, bending moment at that section is maximum, minimum, maximum or minimum, none. You see here in this case, maximum is correct, minimum is correct, maximum or minimum is more correct. So, this you have to answer. Either they can ask you like this, shear force is 0 at a section, bend moment at that section is maximum or minimum, or m is constant. Another way of asking is this one, or m is constant. Either way they can ask. Maximum minimum types means either options can be in this form or it can be in this form. In one gate paper, in this form, 4 options were given. Another gate paper, this is given as one of the option. Then maximum or minimum will not be there. Bend moment is constant. That means that shear force is this one as 0 at a section, means that bend moment is constant. Okay. Now, supposing that if bend moment is 0, if bend moment is 0 at a section, shear force at that section is. Now again same options, maximum, minimum, maximum or minimum, none they will not ask you, nothing is known about shear force, some hint they will give you. Now you see in this case, as you have learned, if bend moment is 0 at a section, shear force is neither maximum nor minimum, some intermediate value. Nothing is known about shear force. Why nothing is known about shear force? This is the reason. See here, explanation for that is this one. dm by dx is v. If v is 0, then we can tell something about m, minimum or maximum. If m itself is 0, then d0 by dx can take any value. If m is equal to 0, we cannot tell anything about v. Okay. So, this comes from this expression. Now, you see, we have applied the end moment distribution for two spans A, B, B, C. You locked them, you unlocked one by one, you finished the problem. Why should we unnecessarily lock them, then unlock them and waste our time? Because that only we know. An unknown problem you are converting into a known problem. What it means is converting an unknown problem into a known problem. See here, a 2 marks question they asked once for a single span itself, like this. Moment at A is, they have given one propped cantilever beam. There is a hinge support, some was there. This is the load W. This span is A, this is B. We don't know what is moment at A, but what we know is when B is fixed, we know. In this case, the deflection profile we know. Like this. Strength of materials you might have by hearted the formula also. Assume that we have forgotten that formula. So, what we do is, first we will fix it. This is symbolic representation of fixing the joint B. Why should we fix it? Because we know formula for that only. What is MA? W A B square by L square. Here W A square B by L square. This we know. You see here, unnecessarily you fixed it. Now release it. Releasing means what we have to do? You apply anti-clockwise moment. This is W A square B by L square. This opposite direction movement we call it as release. You release it. We only went and applied this much moment. You unnecessarily applied W A square B by L square. You have again applied another moment. So, that net moment you applied how much? 0. So, moment here is also 0. Moment here is 0. So, 0. So, what you have done? First fix, then we know what is the moment, then release. When you release it, how much moment is carried over here? Half of that, W A square B by L square. Now, you see, I can add these two moments to get the final end moment. That is the process. So, this is your MAB. So, MA is this plus this. Moment at A. This I remove. So, moment at A means this is W A B square by L square plus half of W A square B by L square. Common factor we can take it as W A B by L square. Here B plus half of W A. How much is left out here? b plus a by 2, WAB square by L square, common factor half WA square B by L square, AB by L square, here B plus A by 2. So, this we can write it as 2 common factor if I take it out, WAB by 2L square into 2B plus A, 2 when we take it out 2B plus A we can write. A plus B is nothing but L. So, this we can write it as MA is equal to WAB by 2L square into B plus A is L plus B. See, now to remember this one is very difficult, WAB by 2L square into L plus B. If you without understanding, if you by heart it say, then you may forget that formula, whether 2 should be kept in the denominator or numerator. Shall we write plus or minus? Because so many formulas you have by hearted. In that one formula is attached to some other formula, let us say, then gone. This way, very simple, fix, release, carry it over. No question of forgetting any formulas. These are so basic, AB square by L square, A square B by L square. Remembering them itself is fine, and whose end result for each case like that, if you have to by heart, means it will so much heavy load on our brain that we will be frustrated. We will feel that okay, why this subject, we will leave it off. But if you know how to get the results also within 10-15 seconds time, you will enjoy them. Means that is the way you have to solve the problems. Where if there is no such logic, this formula, if you have to by heart it and answer, they will never ask such questions. One of the option is this one, but they will never ask if there is no logic at all to get that result. Okay, be assured about it. You don't have to by heart so many formulas, only basics if you by heart, then other things you should be able to derive like this. Okay, next, if you see the deflection profile of this problem, how to get that deflection profile is like this. For any problem, this is the way we have to draw the profiles. So, this is our beam. Okay, up to here, this is sagging. See here, positive endowment. From here to here, it should sag. Up to here, it should hog. Then this should sag. So, positive endowment, you got it. Sag, hog, sag. Now, how we should manage this? We should not remove the supports at A, B and C. Okay. Now, up to here we must sag it, this should hog. So, when it is hogging, we can show it like this. This hogging, this is sagging. This is point of inflection. At the point of inflection, deflection can exist, but the way we have drawn, it looks as if it is touching that point, but does not matter. It is sagging. This is sagging, this is hogging. It is a smooth curve always. So, when you drop a tangent, theta must be same. This is theta b, say. This also theta b. It should be a smooth curve. Like this. Okay. Sagging, hogging, sagging. So, this is your deflection curve. This point where bending moment changes its sign, you call it as POC, point of contraflexure. In this curve, where the curvature changes its sign, we call it as point of inflection. Point of inflection is more general term. Wherever curvature changes its sign, it is called point of inflection. Not necessarily because of bending moment, any curve, any mathematical curve changes its curvature, then that is called point of inflection. But it so happens that if at all bending moment changes its sign, because of bending moment has curvature form expression also, so it is a particular case, that's all, where bending moment changes its sign. At that point there will develop one point of inflection in the beam. So, on the deflection profile where curvature changes its sign, we call it as point of inflection. On the bending moment diagram where bending moment changes its sign is called point of contraflexure. Contraflexure term we show in the bending moment diagram. In point of inflection we use in the deflection profile. Okay. So, if they ask you a question, once they asked in the civil services, where bending moment changes its sign is called point of inflection, point of contraflexure, like that they asked. Point of inflection we should not answer, you should call it as point of contraflexure only, where bending moment changes its sign. Okay. So, where we use is, this is in the deflection profiles, this we use it in the bending moment diagrams. Okay. So, this is about the complete information about the moment distribution method. Now, we will see after this a frame with both ends with fixed support, how we should manage the moment distribution for the frames.